So today we're going to focus on homework 5. So the first question asks that find the smallest positive integer x such that phi of x equals 6. So the first thing we should do is rewrite this with the prime factorization. So instead of writing x, let's write this as phi of p1 to the a1, p2 to the a2, all the way to pn to the an. Now we know this quantity has to be bigger than one of its respective primes, greater than or equal to p1 to say a1, which is going to be greater than or equal to phi of p1, which we know with our formula has to be p1 some prime minus 1. So that's p1 for notation. But we also know this number all the way here has to equal 6, given from the problem. So using our inequalities, we can rewrite this as p minus 1 has to be less than or equal to 7, or sorry, 6, which means that p has to be less than 7. So this tells me all the primes that divide into x have to be less than or equal to 7. So that gives me 2, 3, 5, 7. So what it's telling me is that x is some form of 2 to the a1, 3 to the a2, 5 to the a3, 7 to the a4. So some number with some varying exponents. So I at least have the form down. So I need to figure out the exponents such that I can minimize this to get the smallest number. So our approach is, well, we know x has to equal 6, or the phi of x has to equal 6. So two ways I can do that is either 1 times 6 or 2 times 3. So the way I approach this is using the multiplicative nonsense. So I can say, if I take the phi of x, I can take the phi of each of these prime powers respectively. So 5 to the a1 times phi of 3 to the a2, phi of 5 to the a3, times phi of 7 to the a4. Now let's recall that if we're taking the phi of some prime to some exponent k, that's equal to pk minus 1 times p minus 1. So let's apply that for each of these powers. So this gives me 2 to the k minus 1 times 1, 3 to the, this a1, 3 to the a2 minus 1 times 2, 5 to the a3 minus 1 times 4, and 7 to the a4 minus 1 times 6. So again, I need two factors from this set such that when they multiply, they equal 6. And 2 because it's either 1 times 6 and 2 times 3. Well, for 1 times 6, I'm really only looking at 6, right? So that means that I just need one of these factors in brackets to equal 6. So your hint is that it's obviously going to be this one, right? So that means what a4 has to be 1 to make this drop down to 7 to the 0th power, which is just 1. But if a4 is 1, that means I can't multiply by anything else. So that means these exponents up here must be 0 such that all these phi's are just go away. So I'm only dealt with 7 to the first power, which means I'm taking phi of 7. So if we think about it, remember 7's a prime number. So our shortcut is phi of 7 is really just 7 minus 1, since the formula is p minus 1, which is 6. So that double checks our answer, because obviously this is going to be the smallest number. So then, yeah, that's pretty much it. I'll try to that. Number 2 asks that find the smallest positive integer such that x, so that d of x equals 6. So again, we're going to do a similar trick to as before, as we're going to rewrite x as the prime factors. So p1 to the a1, p2 to the a2, and p to the n, a to the n. So that still equals 6. So now I'm, again, use the multiplicative theory, I'm going to separate this out. So d to the p1, a1 times d to the p2, a2, all the way to d to the pn, an. That still equals 6. So now using this, I can say that, well, 6 is still equal to 1 times 6 or 2 times 3. But we can rewrite these shortcuts as, so using this, I can rewrite this as the next part as, remember it's a1 plus 1 times a2 plus 2 plus 1 dot 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 a to the n plus 1 still equals 6. So remember, that means one of these factors has to equal 1 and another factor has to equal 6. So given that, let's just choose, let's say a1 has to equal 0. So that gives me a 1 here. Then a2 has to equal, a2 plus 1 has to equal 6. Therefore, a2 is 5. Now I'm choosing these two factors because remember, look back to the question. They're asking for the smallest positive integer. So intuitively, to get the smallest number, I have to choose the smallest sets of primes. Hence, I'm only caring about the primes 2 and 3 specifically. So P1 equals 2, P2 equals 3. So that means one combination is 3 to the 5th. That seems kind of large, so let me choose the alternate strategy. 2 and 3. So if I were to trying to do factors, so it's 2 times 3, that means A1 has to equal 1, and A2 has to equal 2. That means I have the form 2 times 3 squared, which equals 18, which is definitely smaller than 3 to the 5th. And then one way I can double check that is, well, what are the divisors divided into 18? 1, 18, 2, 9, 3, 6. So these are 6 divisors. Therefore, 5, 8, d of 18 is 6. So 18 must be the smallest number. So we're done. Looking at number 3, it asks that show that d of n is odd if and only if n is a perfect square. So again, all these primes are coming down back to the prime factorization. So let's rewrite n as the prime factors. So d of p1 to the a1, p2 to the a2, all the way to the pn to the an. So again, with a multiplicative theory, we can say d to the p1 a1 times d to the p2 a2 times d of pn to the an. But remember, this is squared. So if remember that n is a perfect square. So if we square it, it's d to the p1, 2 to the a1, p2, 2 to the a2, dot, 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 p to the n, raised to 2 to the n. So you notice it's still going to mirror what we had before, but now we're just raising everything to a square power. So d to the p1, 2a1, times d to the p2 to the 2a2 times d of p to the n to the n. Now we're almost done. So let's recall that if we're taking d of some prime to the k power, that is just k plus 1. So let's recall that for in case you forgot. So if we're doing all the divisors divided p of the k, we can just list them out. It's 1, p squared, dot, 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 all the way p to the k. So now just treat k as your new exponent here. So that's 2 to the a1. So here we're just going to get 2 to the a1 plus 1 times 2 to the a2 plus 1, dot, 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 2 to the n plus 1. Here we're already done. Why is that? Because I have a 1 in every single term. So when I FOIL them all out, I'm still going to have a plus 1. Right? So I'm going to have a grouping of all even numbers plus 1. So as a result, that's going to give me an odd number. Therefore, d of n has to be odd if and only if n is a perfect square. If I look at 4, it asks that mu of n plus mu of n plus 1 plus mu of n plus 2 equals 3. So given this, if I take mod 3 of each side, that's saying that I need mod 3 has to equal what? 0, right? So that means what's a new function? So looking at 4, I have that mu n plus mu of n plus 1 plus mu of n plus 2 equals 3. So let's recall our definition. So if I want to take mu of n, that's either going to be -1 to the w of n or 0. So this is if it's square free, and this is if it's otherwise. So given this information, the only way I can ever get 3 is if I'm summing up 3 ones. Right, because I can't alternate with 1 and -1, and I can't have a 0 since there's only 3 terms. So that means this gives me a couple of pieces of information. First, it tells me all 3 terms have to be square free, and that they all have to be 1, so that omega n has to be even. So with this, let's go to the next step. That indicates that what I'm looking for is 3 numbers such that the omega of n is an even number, and the mu of n, well, as a result, mu of n will give me 1. So going through the prime set, the smallest one will be 33 times 34 times 35. The reason we choose this pair is this will give us an even prime factorization. So that's 2 to the 7, or 2 to the 17 for the 34, 3 to the 11, and 7 times 5. Now, there's actually no clever way to go about this, but the simplest way I can tell you is that, well, we know omega of n has to be an even amount. So with that, we can say that let's just choose 2. So at this point, you just run through your combination of prime numbers. So like 2 times 3, 5 times 3, 7 times 5, and just go through possible combination. Go through those 2 pair multiplications, and then find the 3 consecutive integers within that range, and see if you can find that within that 3 set of integers, such that it's factorized into only 2 primes. So while it's still guess and check, it's not a lot of guess and check since there's only a finite amount of possibilities. So now with 5, it's asked that mu of n times n plus 1 times mu of n plus 2 times mu of n plus 3 equals 0. So this one's not actually a lot of work. So if we notice what the parameters are, n plus 1, n plus 2, n plus 3. So that means that these are 4 consecutive integers. So that implies that 4 has to divide into n, or 4 divides into n plus 1, or 4 divides into n plus 2, or 4 divides into n plus 3. Right? Given one of these facts, that implies that mu of whatever term is that whatever term in here has to be not square free. Why is that? Because a square number, 4, which is 2 squared, divides into that number. Therefore, it has to be 0. And as a result, 0 times anything is going to give me 0.